In this video lecture, we will discuss one of the basic topic of fluid mechanics, manometer. First of all, what is manometer? So manometers are defined as the devices used for measuring the pressure at a point in a fluid by balancing the column of the fluid by the same or another column of the fluid. Here we are considering the datum line, to measure the pressure of the fluid. They are classified as simple manometer and differential manometer. In this video lecture, we are only discuss simple manometer. In next video lecture, we will discuss differential manometer. First of all, what is simple manometer? A simple manometer consists of a glass tube having one of its end is connected to a point where pressure is to be measured and the other end remains open to the atmosphere. Here you can see that one end of the glass tube is open to atmosphere and the another end is connected to the pipe where pressure is to be measured. Some common types of manometers are piezometer and U-tube manometer. In this video lecture, we will discuss piezometer, U-tube manometer and single column manometer. What is piezometer? So in piezometer, it is a simple device. Here you can see one end of the glass tube is connected to the pipe and the another end is open to the atmosphere. Here we are considering the point A where we want to measure the pressure. The height of the liquid, say H, in piezometer tube, their pressure at A. And we know that according to hydrostatic law, P equal to rho GH. Pressure is depend on density of the fluid. G means gravitational acceleration and H is the height. Its unit is Newton per meter square. The unit of the pressure is Newton per meter square. So by using this device, simple device, you can measure the pressure of the fluid at point A, P equal to rho GH. The second one is simple U-tube manometer. Here we will discuss two cases. The first one is gauge pressure and the second one is vacuum pressure. Gauge pressure means the pressure above atmospheric pressure. Here the pressure is high in pipeline B. And here we are considering the negative pressure. The tubes generally contains mercury or any other liquids whose specific gravity is greater than the specific gravity of the liquid whose pressure is to be measured. The first case is gauge pressure for simple U-tube manometer. Let B is the point at which the pressure is to be measured whose value is P. In some of the reference book, we are considering PB instead of P. The datum line is AA. Here you can see that, here we are considering datum line to measure the pressure at point B. Let H1 is the height of the liquid above the datum line in left hand side column, or we can say left hand side limb. H2 is the height of the liquid above the datum line in right hand side column. S1 equal to specific gravity of light liquid. This is a light liquid like as kerosene, water, and this is the high dense liquid, which density is higher. Generally we are considering mercury. So S1 is the specific gravity for light liquid. This is a light liquid. Rho 1 equal to the density of light liquid equal to 1000 into S1. We know that specific gravity means it is the ratio of unknown density upon standard density of the fluid. And it is a unitless term. Specific gravity, it is a unitless term, and its value is required to calculate the unknown density from the standard density of the fluid. For liquid, we are considering water as a standard fluid, and for gases, we are considering air is a standard fluid. So from the value of the specific gravity, you can calculate the density of unknown fluid by multiplying with the 1000 value for liquid. And for gases, we are considering air as a standard fluid. S2 is the specific gravity of heavy liquid. This is a heavy liquid or high dense liquid. Rho 2 is the density of heavy liquid equal to 1000 into S2. We have already discussed. Okay, whenever we multiplied specific gravity with 1000, because 1000 it is the standard density for water. So rho 2 equal to 1000 into S2. So you can calculate the density of unknown fluid, or we can say high dense fluid, if it is not given in the data. The datum line is AA. Here we are considering datum line is AA. So the pressure above AA in the left column equal to P. Here we are considering the pressure in the pipeline B is P plus pressure due to the height of liquid in left column, and according to hydrostatic law, P equal to rho GH. So here we are considering rho 1. Rho 1 is the density of light liquid, G is the gravitational acceleration, and H1 it is the height or height of column in left hand side column, and H1 is the height of column for light liquid. Same for pressure above AA in the right column. Okay, in right column here we are considering high dense fluid, okay, which density is higher than light fluid, left hand side column. So the pressure in the right column equal to rho 2 GH2, or we can say pressure due to the height column H2 equal to rho 2 GH2. Hence equating the two pressure, okay, from the datum line, here we are considering datum line to compare the two different pressure from left hand side and right hand side. Now we will compare pressure in the left hand side column equal to the pressure in the right hand side column. So P plus rho 1 GH1 equal to rho 2 GH2. Further we simplified this equation. So this term it will be shifted from right hand side, so it will become negative. So P equal to rho 2 GH2 minus rho 1 GH1. So in the example of fluid mechanics of manometer, by using this equation, okay, you can solve the example and you can calculate the pressure in the pipeline for simple manometer. Second case, here we are considering vacuum pressure. We know that what is vacuum? Vacuum means the pressure below atmospheric pressure. Okay, so here the pressure is negative or below atmospheric pressure, so it will suck the fluid. So here you can see that, okay, pressure above AA in the left column equal to rho 2 GH2, means the pressure due to the height of column of mercury or high dense fluid, plus rho 1 GH1, pressure due to the height column of light liquid H1, which height is H1. So rho 1, which is the density for light fluid, G is the gravitational acceleration, and H1 is the height for light liquid column, plus pressure in the pipeline. Here we are considering P or PB. It is the pressure in the pipeline B. So this is the pressure in the left hand side column. Due to the suction, due to the negative pressure in a pipeline B, because here we are considering the vacuum pressure, so here it will suck the fluid. So there is no any fluid above the datum line. Here we are considering the datum line is AA. So on right hand side, the pressure head in the right column above AA equal to 0. Now we will compare the pressure for the right hand side and left hand side. Here we compare or equating the values of pressure in the right hand side column equal to left hand side column. So rho 2 GH2 plus rho 1 GH1 plus P, which is the pressure in the left hand side column of a single column manometer, which is the pressure for, so rho 2 GH2 plus rho 1 GH1 plus P, which is the pressure in the left hand side column of single U-tube manometer equal to 0, because here there is no any fluid. The pressure above datum line in the right hand side column equal to 0. Further, we simplified this equation, and now we will make the object P, and this term is shifted right hand side, so it will become negative. So P equal to minus in bracket rho 2 g H2 plus rho 1 g H1. Here this negative sign will represent the negative pressure or pressure below atmospheric pressure. Now we will derive the equation of pressure for single column manometer. There are two types of single column manometer: vertical single column manometer and inclined single column manometer. So here we are considering in first case vertical single column manometer. Here you can see that the column, it is vertical, so it is called vertical single column manometer. Let XX be the datum line in the reservoir and in the right limb of the manometer. This is called reservoir because its capacity as compared to the column, it's so high, so it is called reservoir. Okay, and here we are considering XX be the datum line in the reservoir when it is not connected to the pipe. So it is the initial position of the fluid. So it will represent the initial position of the high dense fluid. When the manometer is connected to the pipe, for example, this manometer is connected to the pipe, due to high pressure at A, the heavy liquid in the reservoir will be pushed downward and will rise in the right limb. So at initial level, we are considering fluid, or we can say high dense fluid, okay, which level is XX. Due to the high pressure in the pipeline, okay, it will apply the force on the high dense fluid and it is fall down, and here you can see that the level of the high dense fluid in the right hand side column, it will be increases. Here you can see that it is pushes downward and will rise in the right limb. This is a right limb and this is reservoir. So the final position of the fluid, heavy fluid, is represented by YY. And delta H. What is delta H? Delta H, it is the height of fluid which is fall down, okay, due to the high pressure in the pipeline. So let delta H, it is the fall of heavy liquid in reservoir. Delta H, what is delta H? Delta H means fall of heavy liquid in the reservoir due to the high pressure in the pipeline A. H2, rise of heavy liquid in the right limb due to the high pressure, okay, it will exert the force on the heavy fluid, so the heavy fluid will be displaced from XX to YY, and here you can see that the level of the liquid in the right hand side column, it will be increases and it is represented by H2, rise of heavy liquid in the right limb. H1, what is H1? H1 is the height of center of pipe above XX. Okay, this is the center of pipe from the reference XX. PA, pressure at A, which is to be measured. Okay, our objective is to measure the pressure at point A, or we can say the device, it is connected with the pipe, okay, and measure the pressure of this pipe. Small a, it is the cross section area of the right limb. Okay, this is the right limb, its cross section area is small a. And capital A, it is the cross section area of the reservoir. Okay, and its cross section area is very high. Its cross section area is very large as compared to limb. S1, it is the specific gravity of liquid in the pipeline. S1 is the specific gravity of liquid in pipe. Here we are considering the specific gravity is S1, and for high dense fluid the specific gravity we are considering S2, or we can say specific gravity of heavy liquid in the reservoir and right limb. Okay, this heavy liquid is present in the reservoir as well as right limb. It is represented by dark pink color. S2, it is the specific gravity of heavy liquid in the reservoir and right limb. Rho1, density of liquid in pipe, and Rho2, density of liquid in reservoir. Now, fall of heavy liquid in the reservoir will cause a rise of heavy liquid level in the right limb. We have already discussed. Okay, here we are measuring positive pressure or high pressure. So it will exert the force on the heavy liquid. So it is fall down from XX to YY, and here the level of the heavy liquid will be increases in the right column of this single column manometer. So from this equation we can write down A into delta H equal to A into H2. What is A? A is the cross section area of the reservoir. Delta H means fall of heavy liquid in the reservoir, equal to A into H2. Small a means area of the right hand side column multiplied by H2, which is the rise of liquid in the right column. So now make the object delta H. So delta H equal to A into H2 divided by A. Now consider the datum line YY as shown in figure. The pressure in the right limb above YY, here you can see that, okay, in a right limb, okay, only one fluid will be present, okay, and its height is H2 plus delta H, okay, H2 plus delta H. Okay, so pressure due to the height column of H2 plus delta H equal to rho 2 G delta H plus H2. Okay, according to the hydrostatic law, P equal to rho GH, and rho 2 is the density of the high dense fluid in the right hand side column. G is the gravitational acceleration. Delta H, it is the fall down of liquid in the reservoir plus rise of liquid in the right hand side column. Same as pressure in the left hand side column, or we can say left hand side limb above YY datum line. So here you can see that the fluid is present. It is a light dense fluid which density is rho1 and height is a delta H plus H1, and plus we are also considering the pressure PA, okay, which is to be measured. So continue from this two equation. Now we will compare the pressure in the right hand side column equal to pressure in the left hand side column. So equating this pressure, we are getting rho 2 G delta H plus H2 equal to rho 1 G delta H plus H1 plus PA. So PA equal to rho 2 G delta H plus H2 minus rho 1 G delta H plus H1. Further, we simplified this equation. Okay, we separate this term, and the common term is delta H from this term and this term. Okay, so it is separate out, and the simplified form of the equation PA equal to delta H rho 2 G minus rho 1 G plus H2 rho 2 G minus H1 rho 1 G. Continue from the previous equation. We have already derived this equation, and getting the value of delta H in previous slide, delta H equal to A into H2 upon A. So put the value of delta H in this equation. So PA equal to, instead of delta H we can write down A into H2 divided by A, and this term is remain as it is. But we know that as the area is very large as compared to A, okay, the area of the reservoir is very large as compared to the column, right hand side column of the single column manometer. So hence ratio A by A becomes very small and can be neglected. So this term is multiplied with this term, so it is neglected because it is very small. So PA equal to H2 rho 2 G minus H1 rho 1 G. So this is the equation of pressure for vertical single column manometer. The second case, we are considering inclined single column manometer. So instead of vertical tube, here we are considering inclined tube. So it is called inclined single column manometer. This manometer is more sensitive as compared to the previous manometer. Due to inclination, the distance moved by the heavy liquid in the right limb will be more. Let L, what is L? Length of heavy liquid moved in the right limb from XX reference line. Okay, same case we are considering. It is the initial position of the high dense fluid due to high pressure. Okay, it is fall down, and the final position of the high dense fluid is YY. Okay, here the level of the high dense fluid it is decreases, and due to this the level in right hand side column it is increases. Okay, so L is the length of heavy liquid moved in right limb from XX reference line. Theta, it is the inclination of right limb with horizontal. Okay, with horizontal reference line we are considering the angle theta. Okay, because it is the case of inclined single column manometer, and theta it will represent itself inclination of right limb with horizontal. Okay, and H2, this is H2, vertical rise of heavy liquid in right limb from XX datum line equal to L sin theta, because sin theta equal to in front side upon diagonal. So in front side is H2 and diagonal is H. So sin theta equal to H2 by L. So H2 equal to L sin theta. So from equation, the pressure at A, which is to be measured, and H2 equal to vertical rise of heavy liquid in right hand side limb from XX equal to L sin theta, we have already discussed. So PA equal to H2 rho 2 G minus H1 rho 1 G. Pressure at A equal to rho 2 H2 G minus H1 rho 1 G. Substituting the value of H2, we are getting, okay, here we will put the value of H, okay, because this is the same case of single column manometer for vertical case, but here we are considering incline. So due to inclination, okay, the sin theta is there. So first of all, here we are getting the value. So here first of all, here we are calculating the value of H2 and put the value of H2 in previous equation of single column vertical manometer, because here we are considering inclination. So our objective is to calculate the height H2, okay, in terms of sin theta. So put the value of H2 equal to L sin theta in this equation. Okay, we have already derived it in previous slide. So substituting the value of H2, we get PA equal to, instead of H2, we can write down L sin theta into rho 2G minus H1 rho 1G. Thank you friends for watching this video. I hope this content it will be helpful to you. If you would like to watch this type of more technical videos, then please subscribe our channel and also share with your friends.